want to look at a problem where we change the order of integration. So we're trying to integrate the function 12y squared z cubed sine of x to the fourth, and we're doing it in the order with respect to x, then with respect to y, then with respect to z. So our limits on the x are from y to z. So x is bound below by y and above by z. Now that's looking at two planes, x equal to y and x equal to z. So those are the planes that are the bounds for the x. Now the bounds for the y are given by 0 and z. So that means that y is bound below by 0 and above by z. So think of that as two planes. That's y equal to 0 and y equal to z that are the bounds for the variable y. And then finally, our variable z is bound by just the constants, 0 and the fourth root of pi. So if you want to think of that as z equal to 0 and z equal the fourth root of pi. Now, because those are already constant values, if I were going to change the order of integration, I would try to leave the z alone because that one I know is already constant values. And then I would try to just flip the x and the y. Now, why would I need to try to flip those? If you look at this function, you're integrating with respect to x. The x's appear in this as the argument on that sine function. So the only way that you're going to be able to accomplish that integration is if you had an x cubed out here, because a u substitution here would be u equal to x to the fourth, and that would require that du, or whatever was here, had to have an x cubed in that expression. So we can't integrate right now with respect to x. So flipping the x and the y would be what we would try to do. Keep the z with the limits from 0 to the fourth root of pi. And now let's see how we could flip it to make it dy dx. Well, to do that, we first need to figure out the limits on the y. Now the limits on the y, if you were able to look at this solid, the limits on the y will be what you get by taking a ray parallel to the y-axis and passing through that solid. And you'd want to figure out what the upper and lower bounds on the y would be. Now let's see, it's kind of difficult to actually view this solid in 3 dimensions in a two-dimensional picture. So let me look at it algebraically. I have that x is bound between y and z, and I'm trying to get the bounds on the y. Well, I can see here that y is bound by x and z. Y is less than or equal to x, less than or equal to z, and this one tells me that the y is actually greater than or equal to 0. So if I were looking for bounds of y, and they can be in terms of x and z since those will be integrated later, y is between 0 and x. So let's put that y is between 0 and x. So now, what about the limits on the x? Well, again, combining these, I see here that the x is bound above by the z, and x is bound above by the y. But by the time we integrate with respect to x, we've already integrated with respect to y, so we can't use y in the expression, but we can see here that the y is bound below by 0. So our x value then would be bound by the 0 and the z. And then our function remains the 12y squared z cubed sine of x to the fourth. But now if you're integrating with respect to y first, here's the only y in that expression, so the rest is just a constant. Okay, so integrating with respect to y, we'll have 12 z cubed sine of x to the fourth, which is a constant, times y to the third over 3. So that would just make that 4. And we evaluate that from 0 to x. And then we still have our outer integrals. Okay. Evaluating by letting the y be x, we would have 4z cubed. Now I'm putting x in here, so I'm going to have an x cubed sine x to the fourth. And now when I put 0 in for the y, we would just get 0. And you can see now that we're going to be able to integrate next with respect to x with no problem. Okay, so now looking at the x's, we have this x to the fourth, and we have the x cubed here. So if you were making a substitution, u equal to x to the fourth, we now have the x cubed, which is part of the du. We would have to add a 4 and then multiply by 4 and then divide by a 4 to be able to do that u substitution. So I'll have, if I put a 4 in there with that x cubed and then divided by the 4, this then is sine of u, and this will be part of the du. So I'm now going to have just z cubed, which is still a constant, and then I'm integrating sine of u, which will just be negative cosine of u. But the u, remember, is just x to the fourth. So I've done the u substitution without actually making the substitution. But now we evaluate from 0 to z, letting the x be those values. And then we still have the outer integral 0 to 4th root of pi with respect to z. Okay, so now putting x equal to z, we would have and then when you evaluate at 0, we'll have cosine of 0, which is 1. So we'll have minus a negative, so it'll just be plus a z cubed. Okay, so now integrating with respect to z, again, we let u be z to the fourth, and we would need to have a 4 out in front here, and then divide by a fourth. So that's going to give me, and I'll pull the negative out, that's going to be a negative 1/4 sine of z to the, actually it'll make it another negative since the integral, no it's not. Now this 1/4, I shouldn't have put it out in front of this whole thing because it's not in front of this term. It's only in front of the part that had the cosine. So we put it over here. Okay, so now we're evaluating from 0 to the 4th root of pi. So that's negative 1/4 sine of just pi plus 1/4 and then just pi. And then when you evaluate at 0, everything would become 0. This is 0, so the answer should be just pi over 4. Okay, so when you're trying to change the order, be sure you first write down what your ranges of values are for each of the variables based on what these limits of integration say. X goes with these, Y goes with these, and Z goes with these. And then you can use this algebraically without even having to worry about the picture sometimes to figure out what your bounds are. When we switch to Y, we could use this to get the upper bound for Y and the lower bound for Y. And likewise for the x, we can see that x is bound above by the z, below by the y, which was also bound below by the 0. So just make sure that the limits on x can't contain y. Um, the limits on y can contain x and z. The limits on z, of course, can't contain anything but itself by the time we get to that point.